So we're in week 2. We took a little introduction to what calculus 1 and 2 are like, the two main problems, and started playing with limits. So we're going to continue that play with limits and then develop a bunch of limit laws. Those limit laws relate to continuity, and most of the work we're doing in section 2, 2, 2, 3, and even 2, 4, it's kind of an intuitive version of this kind of mathematics. And then so we're going to get to what I call the precise definition of a limit, or the formal definition of a limit at the end of the week. And that solidifies how these limits work to ensure that we have results that are reliable. In the meantime, we're just gonna collect a bunch of tools. So kind of like, you know how to solve equations quite well, and you can look at an equation and decide whether you need to add, subtract, multiply, divide, take a square root, maybe use a logarithm when you're trying to solve for a particular variable. And we're going to develop a bunch of rules like that related to limits. So let's get busy. So this is section 2.2. And the kind of limits we're working on right now are really kind of intuitive limits. And you already have a lot of experience with this, and we'll look back on some of that experience today. So some examples we looked at before, or at least similar to before. Let's take a look at the limit as x approaches 2 of x squared minus 4 over x minus 2. And I mentioned the other day, if you plug in, that's kind of cheating. So let's cheat here and see what happens. If we cheat and let x equal 2, then we're going to get 2 squared minus 4 over 2 minus 2, which is 0 over 0. And I mentioned last week that this is an idea in math that we call indeterminate. Sometimes there's an actual value to 0 over 0. Sometimes it's 1, sometimes it's 0, sometimes it's 2, sometimes it's 4, sometimes it's infinite, all over the map. So more work needs to be done in this case. If we ended up with 1 over 0, we're done. There is no answer. But here we have 0 over 0, it's indeterminate. So what we did was we said, okay, this right here really says x approaches 2. And the fine print about the approaches there is don't touch, which we did above. Sometimes it works, sometimes it doesn't. So there's a couple of ways to proceed from here. So one way we did in class the other day was make a table, and a spreadsheet's a good way to do this, because what we want is to repeatedly plug in numbers close to 2, like 1.9 and 1.99 and 1.999. And we also want to look on the other side, 2.1, 2.01, 2.001. And we want to see what's happening with these y values. Is there a pattern that we can identify? So that's one way we can approach this numerically. And we'll do that in just a moment. The other way we can try is maybe there's some algebra we can throw at this, which we did last week also. So you might notice that the numerator there is factorable. X squared minus 4 factors as x minus 2 times x plus 2. And since we had a denominator of x minus 2, those factors of x minus 2 factor out, simplify. What does that mean here? Well, I have a number divided by itself, which is 1. 1 times x plus 2 is x plus 2. So this is equal to x plus 2. Well, on the condition that we don't plug in negative 2, because that leads to a different result on the left. However, if we continue to cheat over here and let x equals 2, then we're going to get 2 plus 2 or 4. So we're hoping to see that these numbers right here are heading closer to 4 when we look at that numerical pattern. We look at the graph to also check this out. So we have a bunch of things on our side. We have numerical tables we can build, maybe we can throw some algebra at it, and we also have these powerful graphing utilities. So let's use Desmos for fun today. For GeoGebra, it's a little more powerful, more tools, but it's also harder to use because it has more tools. When using something like GeoGebra or Desmos, I recommend using function notation. So I'm going to use f of x here, and I have a fraction x squared minus 4 over x minus 2. And it looks like a complicated rational expression algebraically, but graphically it looks like a line, and we verified that it is indeed a line when we simplified it. So my original expression here, for all values of x except x equals 2, is the same as x plus 2. So they disagree only when x equals 2. Otherwise, these two agree on the y values, the results of plugging in an x value, the output. And so we can see, if we zoom in a little, that as x gets close to 2, the y values appear to get close to 4 here. So it looks like we have the point 2, 4 on this graph. All right, so I could plot the point 2, 4 and see that, hey, it sits right where my algebra said it should. But if I ask the computer, hey, what is f of 2, by the way, the computer says it is undefined. So let's look at another example. How about call this g of x, and it's going to be, oops, equals, parentheses, 1 plus x raised to the power 3 over x. And let's turn off this other one. That point. All right, so I have this new graph right here that I want to take a look at. And what I'm curious about, I'm going to zoom out a little bit. Let's see, did I type that right? I did. I want to see what's happening when x equals 0. So you can see over here that for positive small values up to a point, looks like maybe around 20, it crosses over. So again, what's going on there? So we have a graph we can look at. And if we click on the graph in Desmos, Desmos nicely usually shows us intercepts, but it can't show that one. So we'll have to throw it in there. So we can plot points by just starting parentheses. I want to know the point 0, comma, g of 0. So function notation can be really handy. And interesting, Desmos is having a hard time with this. It's undefined. Oh my goodness. So we've got some work to do here. So it looks like there should be a point there, but Desmos can't seem to graph it, and it definitely can't calculate it. So let's go to our workbook, our notebook. Hopefully you're writing this down too. We have another problem. So we are looking at the limit as x approaches 0 of 1 plus x in parentheses raised to the power 3 over x. And I tried to cheat the limit by just plugging in x equals 0, and I got 1 plus 0 raised to the power 3 over 0, and up here I have a problem. Uh-oh, I have 3 over 0, which is undefined. So I have 1 to this power 3 over 0. So I've got some work to do. So graphically, it looks like near 20. So graph seems that y is about 20. I didn't really zoom in to double check that, but that's kind of a ballpark guess. Just looking at the graph, we need to build a table of numbers. X and y equals 1 plus x to the power of 3 over x. And we need to plug in numbers close to 0. So on one side, we would do, say, a tenth, and a hundredth, and a thousandth, and maybe further. And we also have to look at the other side, so negative, because limits don't always match on each side. We have to confirm that. So we have to look at the right side of the limit and the left side of the limit. And a calculator is a pretty slow way to do this because you have to do it one value at a time, unless your calculator is a table function like a TI, but I don't recommend buying a TI calculator if you don't already have one. So I'm going to jump into my Google Sheet. And let's see, I already have a spreadsheet started with limits. And I'm going to build a new one, start from scratch. So I'm going to look at the right side first. And I have x versus y equals parentheses. And I usually like to type what I'm doing here so I can look and see later if I come back to it. Raised to the power of 3 over x. And is that big enough for y'all to see, or should I zoom in some more? Okay, thank you, Cole. So right side means I'm on the right side of 0, so positive numbers. So 0.1, 0.01, 0.001, and sometimes just a few like that. I can see the pattern. Sometimes I have to go for a while to try and find a pattern. It just depends on the situation. On this side, we're going to type the expression using the number to the left as the x value. So equals to type a calculation, parentheses 1 plus, then click on the x value adjacent. Continue to enter the rest of the expression. Parentheses are essential here. And once I type it once, Google says, hey, you want me to fill that down for you? And I can say, sure. Does it always do that correctly? The answer is no, but I think it did here. And it's just plugging in the x value. And I can see I'm getting a number close to 20. Is it 20? Well, I guess I haven't gone far enough to see that. So here I could type an equation that says, hey, I'm dividing by 10 each time to get the next number, right? 1/10 divided by 10 is 100th. 100th divided by 10 is 1,000th. So sometimes you can find a formula for the numbers you're plugging in, but you could just be kind of randomly plugging in numbers closer and closer to 0. But a system is always a good idea. I'm just going to type on this time. 0.0001, 0.00001, and we can fill down these numbers and see what's happening. So I can see some decimal places are getting fixed here as I come down. So the 8 seems to be fixed in the next 2. That's a 2, that's a 5. So it looks like I have 2 decimal places. I'm accurate maybe to the nearest hundredth here. So maybe I'll go one more time just for fun. All right. Yep. So on the right side, yeah, so maybe I have 3. Maybe it's 20.086 to 3 decimal places. So let's look at the other side. The other side would be basically these numbers, but negative. So 0 is negative 0.1. And I'm going to do this in an easier way so I don't have to type so many zeros. I'm just going to say take the number above, divide it by 10. And then if I fill that formula down, it'll just keep dividing by 10. And I'm sure you've done stuff like this on a calculator where you just keep hitting divide by 10 equals, 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 equals. So it's a similar idea. And then I can fill this down. And since there was no number here, it treated it as 0. And it says, hey, you cannot divide by 0. So I already knew that. And this kind of confirms, it looks like it's going, notice the decimals aren't exactly the same on each side. And we can see when we look at the graph that this graph is definitely not symmetric about the y-axis. So we should expect to get some different results on each side. But it looks like to 3 decimal places, we have 20.086 is what we're aiming at right there. So So when we put these two together, it looks like the limit is approximately 20.086. And we could double check graphically on that by just plotting that point and seeing what happens. So if I come over here where Desmos couldn't plot it before, I could plot the point 0, 20.086 and see if it looks about right. So I could just kind of use the wheel on my mouse to zoom in there. And yeah, that's about where it crosses, right? You can see above the point, the graph is to the left of the x-axis. Below that point, it appears to be to the right. So more zooming in might help there, but I think we've got an approximate answer here. Will we ever know the exact answer? The answer is sometimes no. If someone says, hey, I need a more exact result, and I say, okay, how exact do you want? And they'd say, well, I need you to get me not to the nearest, so what do I have, tenths, hundred, I have the nearest thousandth here. If somebody says, get me to the nearest millionth, then I would have to search my list, keep building it down till I got close enough. And we could certainly try to do that here. And eventually, though, I'm going to run out of the precision of the calculator. So my Google calculator and the spreadsheet ran out of decimal places here. So sorry, I can't calculate that. It looks like 0 to me. And looks like we have that 5 seems to have stayed the same for a little bit. So now we have 4 decimal places. And how long did it take us to get there? Tenth, hundred, thousandth, million. Let's see, I can't count. Tenth, hundred, thousandth, 10,000, 100,000, millionth, 10 millionth, 100 millionth, billionth, 10 billionth. So I had to go within a 10 billionth of 0 to get 4 decimal places. There is no intercept here. So Cole says if you zoom in far enough, you'll see the intercept. And that's a good point. If the intercept exists, and in this case, it does not exist. Let's see, get my pen out here. There we are. F of 0 here is equal to 1 to the power 3 over 0, which is undefined. So that means there is no y-intercept here. Doesn't exist. So just because we have a limit doesn't mean that at that x value, there's actually a function value. So there is no function value here. Yeah, so Desmos is wrong. So we are exceeding its power to compute. So Cole writes that if I plug in 0.00000003, I get 20.86. And so again, Desmos is incorrect. Well, I guess it is correct in that sense. So let me see, can I copy that? I think so. And let's squeeze it in right here. Will it paste? No. All right, how many zeros did you have? Yeah, you can zoom in and get closer and closer, but we can never get exactly there. So again, back to my spreadsheet calculations. Google must be saving some values because notice these differ a little bit, but now they're going a little up and down, right? It's having some trouble. So this right here, this section, there's lots of calculation errors going on. And how computers make calculation is a whole nother issue that's kind of a different math class. But this region right here are calculation errors. We've exceeded, oops, the ability of our computer to make this calculation. Calculation errors. And almost any calculator you use, Desmos, GeoGebra, Microsoft Excel, a TI, you can't easily exceed what its ability to calculate is just because of the way the computer programs are written to do such things and the storage that's involved to do so. Okay, let's move on.